Okay, looks like we're ready to go. And you guys can see it. Hopefully those online can see it. And we will have a question and answer box alongside that I should be able to read. If you see me walking forwards away from or towards the camera, it's probably because I'm struggling to read the questions. But I will put the offer out there that if people online have questions, just fire them up as we go, and I'll either answer them as we go, depending on what they are, or save them for the end. Okay, so moving from the AGM to the presentation, you've probably all read by now that I'm here to talk tonight about the update process that's underway, looking at the seismic assessment guidance that we use for concrete buildings in New Zealand. There we go. So yeah, it's probably particularly in the Wellington market, teaching people to suck eggs to point out that we currently have two versions of the assessment guidelines we use for concrete buildings. Part C5 of the broader document, the red 2017 version that's used for assessments required by legislation, so most commonly earthquake-prone purposes, but also potentially change of use situations. And then the somewhat more recent, but scarily still 5 to 6 year old yellow version that's probably used for the majority of assessments. The age of that, or both parts really, but in particular the 2018 yellow version and ongoing research and use of those guidelines in the time since prompted the snappily named JCSAEB, the Joint Committee on Seismic Assessment of Existing Buildings, or Joint Committee most commonly, to identify the need to re-look at those guidelines and identify where updates were required. And so that's sort of how I come into things, that my company Compusoft put a proposal in to take that idea forwards and develop proposals for changes to this document that we'll talk through tonight. Just sidetracking briefly, I guess, to put the Joint Committee into context. Many of you will have come across the Joint Committee previously or seen this sort of slide in other presentations or at the NZSCE conference last year, I think. But essentially, the Joint Committee was re-established in early 2022 as a body to oversee maintenance and review of our assessment guidelines, to look at areas where training and further development are required, and to propose work and request funding in those sorts of areas. I say re-established. This body more or less in some similar form, I understand, existed when the current guidelines were developed in sort of 2015 to 2017 period. And the intention at that stage was that the Joint Committee would remain in existence and fulfill these sorts of tasks. But for a variety of reasons, personnel changes, I think, at MB, and perhaps general exhaustion from developing the guidelines, it essentially fell into abeyance for a few years. And it's not until Ken Elwood moved into his role at MB that some energy was put into getting this body back up. There is an intent currently to switch the name of the Joint Committee, or the full name, to the slightly less wordy Joint Committee on Seismic Assessment and Retrofit. That is in recognition of the fact that fairly obviously the committee's not just focused on assessment, it's spilled over as well into the retrofit side of things, and it will please people in the room to know that there are projects underway at the moment to look at developing initially reasonably holistic high-level guidance on the process of retrofitting buildings and legislative requirements and how to go about doing that. So it is, as much as assessment, a real focus of that work. So moving back to the concrete assessment space, and the project I'm talking about tonight has come to be referred to, at least within the Joint Committee, as the C5 Plus project. That plus being because, in contrast to last time in 2018, when the yellow version was published, the focus has been a bit broader, or the scope has been broader. And so we've been proposing changes, or are proposing changes, to part C5 fairly obviously, but also a lesser number of changes to part C1, 2, 3, and also a few for C7. The focus tonight, or the weight of the discussion tonight, is probably around part C5. I'll touch on some changes in C1 and C2, I think it is, which are reasonably far-reaching or significant, and so they warrant some discussion. The changes for C3 and C7 are probably what you'd describe as more procedural, and so they'll come out in due course for public comment. You'll be able to see them then, but probably not of great interest to talk through this evening. The project started off really before the Joint Committee was re-established, with some discussions from some of those involved in the 2018 version, and in light of the recast floors project and people's discussion about how the guidelines were working in practice. So probably about start of 2021, discussions about what needed to be done, how should it be done, and so forth. And then over the sort of 18 months after that, things gradually coalesced until a point where Compusoft, as I alluded to, put in a proposal that was ultimately funded by MB to develop changes, and I'll talk through the process and the oversight over the course of the evening, to talk to how we've got to where we are now, and what the process from here is. And that's obviously of interest, hopefully, to reassure you about the fact that it's not just what Nick says that's being talked about here. It does have a lot of other wise heads providing input, and checks and balances, but also because the Joint Committee now has a number of other projects underway, and further ideas coming down the pipeline as funding and people resources permit. And so the C5 Plus project, in a way, has been a bit of a guinea pig to iron out processes overall, and see how things might be done for future projects. Just going to do a walk. Just read through the question. How do we consider C5 out of Wellington region for a precast concrete? Rather a fairly detailed question. I'll come back to that question towards the end, but see where we get to on time. Some of you, and it may even have been at a previous CSOC AGM or following a previous CSOC AGM, might have seen this photo, which annoys me a little bit because I can't remember the date that I took it, so I can't really find the original photo in my files anymore, but I stumbled on it in a presentation. And I think I put it in there because at that stage, sort of to emphasise that we understood the importance of these documents that we were talking about and had been working on, and the fact that they've really taken on a life of their own in some respects. And percent MBS, as we all know, is not just an engineering term anymore. Stu Oliver had me almost falling off my chair a couple of weeks ago when he sent through another image, which I think is somewhere not too far from here, showing that things have got a little bit more specific these days, and that the advertising no longer focuses just on percent MBS, but which version it's been done to. So these images again are here to say that we do recognise the importance of these documents and the fact that they can't just be changed willy-nilly, and that changes need to be considered and made for good reason. With that said, time obviously moves on. We all learn more things as an industry, as individuals, and that comes both through specific research. I've already mentioned the Recast Floors project, which has informed a lot of the discussions on precast floors that I'll get to later in the evening. International research, we need to keep up to date. And so there's really been three broad reasons, I think, why we've proposed changes for different parts of the guidelines. An obvious one being clarifying and correcting things. There are mistakes. No one's going to be surprised that the existing documents are not perfect. There's subscripts that are wrong, or that are, inconsistent use of notation and things. So I won't be talking about those tonight because they're really quite editorial, but need doing. Then there's the ones that are made, and this, I guess, is really why C1, 2, 3, and 7 got pulled into the project, that the release of the 2018 C5 did generate a bunch of inconsistencies between different parts of the guidelines. The most obvious ones probably being where C5 2018 altered and softened some of the definitions of severe structural weaknesses compared to what was in the red versions. And so you can now end up in a confusing situation of different numbers in different parts of the guidelines. And then obviously we're also looking to update provisions where new knowledge or industry feedback and use of the guidelines suggests that the existing provisions could be materially improved to make them more usable, quicker to apply, and to give a better assessment of what the capacity of a building actually is, which is obviously the main aim of these guidelines. An important point is that while things have dragged on longer than originally programmed, the intent is that this is a short-term project, which basically was taken to mean that we were going to use current knowledge and pull in the research that had been done, what was available, and package it into a format that was amenable to use for practical assessment of buildings, rather than setting off to more blue sky type things of commissioning new research to answer the questions that need, to fill in every gap. So frustratingly, there will be gaps or things that we still know warrant improvement. I'll touch on some of those later, and some of you will groan when you see what they are. We're not proposing changes for those. It's going to be a double or triple negative. It's not because we don't think they're important. It's because the last thing we want to do is postulate improvements based on not a lot of background and find ourselves 3 or 4 years down the track saying, well, we changed from this to that, and now new knowledge says we need to change it again, or we're still not comfortable with that, and get the perception going of sort of flip-flopping and change without rigor behind it. Some here may be aware that I presented this presentation to the Auckland Structural Group last week, and got a text message from Ken Elwood shortly before that saying that MB had caught wind of the fact that the presentation was coming up. I suspect that might have been something to do with the one down here, but whatever it was, he said they're happy with it going ahead, but can you make sure that there's a disclaimer at the start saying this is not finalised content yet. So I texted him back saying, well, we already had the disclaimer, but thought I'd make it flash red and emphasise it a bit. So these proposals are proposals only. We'll talk through the anticipated process to get them towards a final form, but a bit like with the draft TS 1170 that's out at the moment. These are for information and to give people a picture of what's coming down the track. Don't run off tomorrow and start using them for assessment purposes, please. So what is it that we're actually, how are we presenting, or how have we developed things? And I think it'd be nice to say that we're using a reasonably formal process now. And again, I think Ken Elwood's had a lot of input into this across a number of documents and processes of trying to bring a bit more rigor into the way that we go about amending documents and making sure that there's buy-in. And so rather than simply working through a Word copy of the document and tracking in some changes, which we're doing at the same time, but each change that we make, and it's really down to quite a painful level, we're recording into a series of change proposals. And overall, I think there's something like 45 sheets, 45 A4 sheets, admittedly with a bit of blank space like the lines here, but something, couple of hundred overall change proposals spread across the various documents, with each one identifying exactly where in the guidelines it is, cursing occasionally at this the lack of numbering down to low-level paragraphs that makes it a bit harder to do that, but we're stuck with the format we've got there. Setting out a brief summary in most cases of why a change or an issue that's been identified and a reason a change should be made. Then setting out what we're proposing as the change, and then a bit of justification at the back end, where it's something simple and editorial. For instance, up here, aligning part C1 with C5 2018, that's thrown into the table directly. In some of the more significant cases, we've had to write brief documents to set things out over 2 or 3 pages for review purposes or whatever. And so instead there would just have a reference. And so the advantage of this as we talk further through the process is that it means that those in the review and later balloting phases that I'll talk through are really intended and forced to work line by line through each of the changes proposed and actually know that they exist, in contrast to some of the historic situations with standards where changes get made and it's hard for the committees involved to actually know that they're across every single change that's been made through an entire document. Just a couple of questions have cropped up. The one that I've read right through I will answer right now. So there's a question of whether the proposed changes will be in line with TS 1170.5. And I'll answer that question now more to emphasise the position generally that TS 1170.5 is not intended for use for assessment of structures full stop in the foreseeable future. And so for legislative purposes, that's written into the Building Act. So that one hopefully is reasonably cut and dried. But the message really should be at the moment to try and stick with NZS 1170.5 for assessments, even for market purposes. And I can see a few eyes rolling, and I've made similar faces myself. It remains to be seen how that plays out, but that is the intent at the moment. Overall, we're not trying to reinvent things. We're not changing, big high-level frameworks that we use for assessment. We're not throwing much out overall. There's one section that does get a pretty massive change, but this is refinement of what we've got. So it shouldn't have too much overall impact in how you do an assessment. It will affect some outcomes, I think, and we'll come back to that. But the overall process should be similar. The development process has hopefully been reasonably thorough. As we say, these are quite important processes. Compusoft, primarily me, have undertaken most of the sort of dotting of I's and crossing of T's and writing out the change proposals and so forth. But the changes we're proposing have been informed by a number of workshops. People in this room have been at some of those and certainly provided a lot of input here and there. And really importantly, the changes being proposed have been passed over to a review group of subject matter experts, critiqued, sometimes quite vigorously, altered until that group's been comfortable overall with where we've got to. And then we'll come back to the further process from where we are now. But there is a large body of input into what's being proposed. What's anticipated is basically a suite of yellow documents, for want of a better phrase. So this will be a bit of a change in perception, but I think overall it might actually make things seem a bit more logical, where at the moment you've got red assessment guidelines and then this kind of almost orphaned yellow version of C5 that sits out to the side, and confusion resulting. And the intention out the back of the current project is that there will eventually be yellow versions of C1, 2, 3, 5, and 7, hopefully with some identifying year or document number on the front to make referencing easier and to facilitate future updates. And then over time, you might expect to see the suite filled out by other projects. So there's talk of a project or receiving a proposal to update C8 on masonry, and it wouldn't surprise me if people started looking at parts, for instance. So over time, the idea has been floated that we end up with what you might call an earthquake-prone assessment guidance set of documents, the red ones, and then something that you might call phrase like the voluntary seismic assessment guidelines, which would be the yellow version. They have these two related but quite distinct set of documents sitting alongside one another. The questions popped up of why do we need two sets of seismic assessment guidelines? And it's a very good question. The answer basically, I think, comes down to government policy considerations and the fact that there is a strong argument for needing stability, not forcing owners through repeated assessments mandated by legislation as changes are made. But yeah, overall, it would be, from an engineering perspective, easier if we only have one, but it's kind of outside of our hands. So the best we can do is update what we can update and keep fighting the battle for rationalising the system. In terms of an overview of what the rest of the presentation runs through, I'm really focusing on the key changes, or what I perceive as the key, most impactful changes that we're proposing. And I emphasise proposing, not changes that have been made. Most of those, as I say, are focused on part C5. That's where the largest number of changes are. I will talk a little about some changes to C2 in relation to diaphragms, and I think a single change that we're proposing to add into part C1, just because I think it's a reasonably interesting topic. Not a change that will affect day-to-day assessment practice, but probably something that might provoke some thought about what we're doing when we assess buildings. I meant to mention earlier that when I was talking about the various other projects that the Joint Committee's got underway, many of you hopefully will be at the NZSEE conference around the corner from here in a couple of months, where there will be a plenary session talking about the various things the Joint Committee is up to. This project included. The presentations there, I think, will be much shorter than this, but the conference paper, which is, I presume, undergoing review at the moment, can really be thought of as the handout or notes that go with this presentation. So there's a bit more detail on some of the topics in there. So it's obviously not in public hands at the moment, but when those proceedings become available, have a look for that if you're looking for more background to what I'm talking about tonight. Okay, moving into the actual changes themselves, I'll just have a squiz at the another question. Is the draft TS applicable for seismic upgrades of buildings that don't meet the targeted % MBS following their assessment? Good question, and one that I'm not going to attempt to answer here, because I don't know that we have a clear answer on exactly how that plays out at the moment. But, well, sorry, actually, I'll back off on that. The draft TS, the message really is don't use that for design. So whether it's new design or design of retrofit upgrades, the draft, public comment draft, should not be being used anyway. So that's actually reasonably easy to answer. The broader question of beyond the draft, once the final version of TS 1170 is released, I think will be answered in the fullness of time about how that plays into retrofit upgrades, and no doubt will be covered off in a focus of that piece of work I was talking about that the Joint Committee has underway. So I won't look to second guess that, but that's where things are at the moment. Okay, so C1, general issues. And the change that I want to discuss briefly here is really something that we're looking to put in, or proposing to put in, really as guidance to future editors of other sections of the assessment guidelines. And that might sound a strange thing to want to put into the assessment guidelines, but the, I guess, analogy is some of you may have come across at the back of one of the parts, I think it's part of the current version of 1170.5. One of the appendices is basically titled Instructions to Materials Standard Writers. And it sets out some expectations that the 1170.5 committee has for what material standards are meant to do. And so, obviously, engineering capacities, or whatever measure you want to use, are generally uncertain. There's a famous saying about it that I won't try and recall on the spot, but none of them are definitive numbers, or very rarely do we have a definitive number. And so you need to try and have some consistency between how things are defined across the different materials and so forth. So what we've identified in the assessment guidelines is that they don't really provide a fulsome picture of what they're setting out to do currently. The overall aim is obviously to determine or to estimate what the ultimate capacity seismic is. And that's defined in various places as the probable capacity to withstand earthquake actions and maintain gravity load support. And so that makes sense. But the troublesome words in there, I guess, are probable capacity. And as engineers, I think a lot of the time we think probable. Okay, that means 50th percentile, average, or whatever. But there's also sort of a more natural meaning of the word probable, that if someone had asked you yesterday, coming along to the AGM today, and you said, I probably will, that's not a 50-50 normally. It means you've registered, and barring something unexpected happening, you're heading along. The guidelines currently are pretty clear about what they mean for strength. It's written in quite a number of places that expected or average strengths should be used for assessments. But if you do a word search or read through all 1,000 pages, there's really no explicit information given about what's intended with deformation capacities, which seems a kind of strange omission, given that the guidelines are very strong, and I'd say correctly so, on saying that deformation capacity and the ability to displace during an earthquake should be a key consideration for any assessment. So in many respects, it doesn't really matter how strong your building is if it can't move enough to accommodate the earthquake that hits it. What is in the guidelines is the so-called rainbow diagram. And we've interpreted this, and I think got buy-in from most of those that we've talked to about it in the development process. And we think this can be used to really work out what the guidelines think should be going on with deformation capacities. And so paraphrasing slightly, section A 3.2.4 basically says that if you rate a building at X% MBS and then subject that to X% ULS shaking, then the performance should be the same as a minimally compliant new building that was subjected to 100% ULS shaking. And then if you delve into the commentary of 1170, that translates through to, that would mean that the expectation was there was a low probability of injury or death occurring. And that's sort of probably more succinctly shown by the color coding, which once you get your head around it, means that even if you subject a building to twice the shaking that you think it has as an earthquake rating, it should still have a reasonable chance of performing acceptably well and not killing or injuring people. And what we'd propose from that, or what we have proposed from that, is that the guidelines are basically saying that the probable deformation capacity is used in the sense, the more natural sense, that it's a displacement capacity that's likely to be, what you're saying it is likely to be less than the actual capacity. So it's something somewhere below an average value. So the proposed change from that, I'm not going to read through word for word, obviously, but we're suggesting adding a guidance note in section C1, outlining a sort of fairly holistic framework of factors that should be considered when writers of other sections are specifying criteria for working out the deformation capacity of certain elements, and one that we've found quite a useful framework, thinking about some of the criteria proposed in these recent updates. And indeed, really a framework that was in the background when some of the 2018 updates were done. So it's things like, how serious is the failure of an element going to be? Pretty obvious. Is it brittle or ductile? And then maybe slightly less obvious, but equally important, is what's the experimental or other underpinning of the criteria? And so if you've got a huge database, say column tests, think you've got a reasonable handle on the scatter of what's going on, then you can perhaps be a bit more refined, precise in specifying the criteria. Whereas some other things, you've got a much smaller data set, it's harder to impose deformations that you're confident represent what might actually happen during an earthquake. That sort of thing needs to be taken into account. So that's probably as much as I want to say on that now. I'll try and remember to sort of link back to this idea in discussing some of the other things, particularly precast concrete floors later on. But that's where things are. So moving into part C5, and I'll just again pause to look through the questions. Question there, is it really safe to rely on expected material strengths not supported by adequate tests? I think the answer I'd give to that one is it probably depends a wee bit on the material you're talking about and the situation that you're looking at. And certainly, I guess if you were talking about brittle shear failure of an unreinforced concrete element, then and that was really critical to the life safety in a building, then certainly recommending some testing on that might let you sleep better at night. On the other hand, if it's, say, the stereotypical 80s ductile frame and really you're relying on the ability to deform rather than the strength, and also you're probably much more confident that it doesn't matter too much if it's 300 MPa or 324, and the information that the average you're relying on is actually underpinned by a pretty solid base of experimental data. But yeah, certainly never a problem to request material tests, except for trying to get them past the client and the cost and disruption of doing so. So changes in C5, there are obviously dozens of these. I don't know that it quite got into the low hundreds, but would have been pretty close. But there's really probably about 5 or 6, I think, that are worth talking through tonight. It's quite big picture sort of things. And one that is fairly one of the earlier ones in the section and quite broad ranging, I guess, is trying to improve the framework that we use to avoid loss of gravity load carrying capacity in structures. And going back to the definition we talked about, that's obviously a fairly key consideration of the guidelines. It's in the definition of ULS, ultimate limit state seismic, ultimate capacity seismic. And currently, the framework that's in the 2018 version of C5 actually has a couple of things in it that in hindsight we didn't get quite right. The framework used more or less across the board for different element types takes drift limits from US guidance, then typically multiplies those US limits by a 2/3 factor, because in the US they check this sort of thing against MCE earthquake demands, whereas we're comparing them against a ULS demand set, so a more frequent earthquake. And so to have a similar sort of level of reliability to what the US would achieve, we need to back off the limit a bit. And then we've got this additional and slightly hidden away, obscure requirement that says that the drift limit for the loss of lateral load carrying capacity cannot be taken as more than 2/3 of the drift limits at loss of gravity capacity. And aside from the obscureness of that last requirement, which even having been involved in putting it in the guidelines, I often struggle to find exactly where it is because it's sort of hidden away in a few lines of text and not as obvious as it deserves to be. There are 2 other issues that with the current framework, and one is that we've realized there's probably some double counting. So we're being overly conservative or safer than we need to be. So it's better than being unsafe, I guess, but risks pushing unnecessary upgrade for elements. And that double counting comes in because the 2/3 applied is really accounting for the same ULS to MCE type difference, whether it be the 2/3 applied to the US drift limits or the 2/3 ratio between lateral and gravity drift limits. And so there will be it's a double counting in there. And then Conversely, if you're applying the wording of C5 2018 really strictly and trying to wriggle through the system, then there are elements, and they're probably the ones that are most likely to cause a problem through loss of gravity load carrying capacity, that you're not relying on to provide lateral capacity at all. So obviously, very slender secondary columns, perhaps carrying very high gravity loads and catastrophic if they fail, you're probably not relying on them versus the walls or the primary frames. And so you wouldn't technically need to apply that 2/3 factor to them. Same thing with slab column connections that are also known to be a problem. So what's being proposed is to try and address both of those. And basically, after umming and ahhing and trying to work a way through this, it seemed that unfortunately the best way to do it was to introduce some new notation, or propose introducing new notation. And so the proposal now is basically to work out a drift limit for loss of gravity load carrying capacity that would be basically similar to what you might calculate if you're in the US, something that was appropriate to compare to a larger than ULS earthquake. If you want to call it MCE, then call it MCE. Or if you don't like the term MCE, then we'll call it something else. But then to basically take that calculated drift, multiply it down to then be comparable to ULS drift demands in one step. And so we think that's probably more transparent overall, simplifies the process, and hopefully gives it the prominence that it requires. It also allows clarification of how SSWs factor into this thing. A number of the SSWs relate to loss of gravity load carrying capacity for slab column connections and columns and so forth. And it feels both here, and there's a couple of other changes, that if these are accepted, that we end up with a more graduated progression between something where failure is not considered to be too problematic, where you might compare drift limit directly to ULS, so flexural failure of a beam, say, through to something that we really don't want to happen, failure of a column, through to something that we're not too sure when it's going to happen and we really don't want to happen, say failure of a very lightly reinforced and heavily loaded column. And you end up with, you'll still have step functions, but you're not going to jump from a factor of 1 down to a factor of 0.5 and have this huge leap in one go. So it feels like a more comfortable sort of set. Another big omission from the current guidelines is that despite the fact we're looking at older buildings, there's really no references as such at all to what to do if you find an older building that's corroding. That obviously will either affect your project or it won't, but if it doesn't, you're currently in a bit of a hole and left in the dark as to what to do. Fortunately, we've had a couple of different people publish recent research that's quite amenable to inclusion or reference into the guidelines. It sort of fits within the frameworks we use. And so we're going to provide these references to papers by Lucas Hogan and various of his co-authors, Nataraj et al., and also a second paper by Tayo Opobola that really fits more in the US framework of what we call here the direct rotation method, and talks about how corrosion can impact that. Again, we sort of ummed and ahed a little bit about how to do this and decided in the end that I think the Nataraj paper is 20-odd pages or something like that, and quite apart from copyright issues and so on and so forth, it seemed that adding 20 pages to the guidelines that are already 1,000-odd pages long seemed like an unnecessary thing. So instead we're going for a referencing approach, pulling some key bits and pieces, this framework type thing, to try and make sure that the content is in there in a way that's aligns nicely and fits within the existing guidelines, but not bringing the whole volume of information in there. That leads reasonably well into some changes that are being proposed in relation to splices and mechanical connections. There's a number of changes made, most of which are relatively small things. Some will be aware that there's a current quite empirical provision that says if you've got a splice and a column plastic hinge, you reduce the effective splice length by, I think it's 2/3 of the column depth. And talking to various people who know, that was sort of something from a US research project a long while ago that's been in ASCE documents, but the feeling is it doesn't align well with a lot of the other approaches used these days and doesn't have much science behind it. So we're proposing pulling that out. Updating direct rotation provisions for various splice governed elements. Adding in some guidance that ties to the corrosion issue, simplifying information that comes from an FIB document about how splitting cracks impact bond strength. So again, slightly niche information, but for the odd occasion when it's needed, quite useful to have there. And then the one that warrants a bit more discussion is that there's quite a large change proposed to the way that grout sleeve connections are treated by the C5 document. So for those who aren't familiar, grout sleeves are these big, typically cast iron tubes that's normally one end threads onto a reinforcing bar, and the other has a bar inserted into it and filled with a proprietary grout. The aim obviously being to couple those two bars together. And the existing C5 2018 says in one of the sections that these should be treated as a brittle element, that they'll achieve the yield strength of the bar, but not sustain any plastic deformation. We were fortunate at Compusoft to be privy to some testing a few years back where 8 grout sleeves were extracted from an existing building and then subjected to uniaxial tension testing. And then more fortunate that the owner of the affected building was okay with these results being used by the industry and discussed, provided that they were kept anonymous. And compared to a lot of things in terms of testing, it's reasonably easy to anonymize a grout sleeve test because once it's out of the building, it just looks like a grout sleeve. So these 8 were tested, and 5 of them worked really well and yielded the bar, sustained plastic deformation, and the test was terminated when the bar itself ruptured, a distance away from the grout sleeve. Unfortunately, the other 3 didn't work well, and they in fact failed well before yield of the bar even occurred. So 5 out of 8 performed better than yellow C5 said they would. 3 out of 8 performed worse. And the worst ones either pulled out at the threads or pulled out of the grout. So this was, I think, a cutaway view of one of the ones that worked really well. The notation might be a bit hard for people to read, but basically shows that where you've got the bar fully threaded in at one end and the other end's fully grouted, then the situation's good and the system works. The ones that failed prematurely universally had construction inadequacies. And so either the bar was not threaded fully in at the threaded end, and if you don't engage enough teeth, then there's not enough strength to stop things pulling out. Or equally, unsurprisingly, if you don't have enough grout in the other end, then you're relying on a really short length and the bar can pull out at that side. So what's being proposed is to say that the grout sleeves generally are able to develop the tensile strength of the reinforcing bar. So the question came up of what that meant versus the yield last time. So basically, we're saying that grout sleeves as a product are able to actually rupture the bar, yield it, develop 15% strain or whatever, and then rupture the bar. But that the suggestion is that you need to presume that a proportion of those grout sleeves are, in fact, ineffective overall and don't even really develop any reliable strength. It's very hard to say what that proportion should be. And unfortunately, as far as I know, it's very hard to actually test in situ or work out a way to look and see what that proportion should be. And so the proposal is that the guidelines will have basically a commentary note saying that in an initial sense or as a placeholder, that 50% would be a value that you could use, assume that half of them work, half don't. That's based on some statistics analysis of the 3 out of 8 failure and then a proportion I thought we had, maybe I've got a pointer here. Sorry, the people online won't see that, but basically the graph here ran some statistics on those, the 3 out of 8. It's obviously a very small sample from one building. So, you know, if anyone wants to pull more out of buildings, we'd love to get more test data and refine this, but we work with what we've got. Along the bottom, it's the proportion of satisfactory grout sleeves that's assumed, and then up the side, the probability that the actual proportion that are good is less than the indicated value. And so the higher the number here is, the worse the outcome, because if you get up to 50% on the vertical axis, you're saying that there's a 50-50 chance that things are worse than you're assuming. And so it happens if we run up from the 50% number, so we're assuming that 50% is satisfactory, you get about a 25% chance that you're worse than that, which within the framework that I discussed earlier sort of sits around about right. Impact-wise, this will, I think, generally be better than what's there currently. Certainly if you're looking at a wall with a whole load of grout sleeves, analysis that we've done says it's better to have half of them actually able to sustain a decent strain so that you get sort of a plastic behavior going with the wall, rather than having an unzipping type thing. Becomes a bit more tricky with columns or the like, where you might have a smaller number of bars, and questions about how those ineffective ones are distributed around the section. So there's, you know, be an interesting piece of statistical work for someone to do with the right Python skills or whatever to draw up some charts for that, but we've not got there at this stage. Okay, before I move on to the next change, I can see there's a question there. Will chemical epoxy rebar anchors be considered? We'd love to. And it was a question that came up in Auckland as well. I can't remember if I've got a slide in here saying, unfortunately, we're not addressing those. Sort of falls in under the category of stuff we don't have enough information about to deal with properly. So the talk last week did provoke some aftermatch discussions about things that might be able to be got underway to try and address that situation and work towards things. My pithy response to someone's question there was, I think it was someone from Ramsed or Hilty, was, well, if you guys fund a PhD student or 3 to go into that, then we might get the research done, which to some extent is true. It'd be personally, I'd find it a fairly hard topic to get up as a PhD student and look at for 3 years, but it would be a really valuable piece of work if we could get that. So long answer to a short question, but unfortunately, no, we're not going to be able to update or propose any real updates there. Okay, stiffness modifiers. I think I've flagged this in presentations before, and again, some will have seen this graph previously, so apologies. But essentially, there are some contradictions currently in C5 2018 between different parts of the guidelines about what the stiffness of a concrete element might be. In one place, we say to use the modifiers out of NZS 3101, whereas elsewhere, the moment curvature approach with the beta V factor is used to estimate yield deformations, which obviously are linked with the stiffness that arises from that. And then during the development process, I'd sort of totally read past it, but someone pointed out that there's actually also commentary in there saying elsewhere that you shouldn't use moment curvature to estimate the stiffness of concrete elements because it might misguide you. And so we've worked through, this does make or have a potential real impact, as the graph suggests, for elements that would be reasonably typical. You can get quite significant divergence between what NZS 3101 suggests and what moment curvature suggests. And so we are suggesting changes basically around how beta V, this factor that accounts for non-flexural deformations, is used. Currently, it's not specified for use on beams. Doesn't make a lot of logical sense because a column with no axial load is not really different from a beam. And so there will be a proposal that it gets implemented for beams. Also a proposal that it should be combined with the NZS 3101 modifiers, because the beta V factor in conjunction with the moment curvature approach was all calibrated against quite a large experimental data set. So if NZS 3101 suggests something different, then really it's NZS 3101 that's not got it quite right, at least compared to that experimental data. But then a slightly sort of counteracting proposal, I guess, because applying beta V could end up reducing the stiffness of all our buildings. But it's been observed as well that beta V is calibrated for things that crack a lot and yield. Whereas if you've had the privilege of walking through earthquake damaged capacity design buildings, really the beams can be all beat up, but the columns don't have a whole lot of cracking going on. And so it's not particularly realistic to think that their stiffness has been reduced to the extent implied by that beta V factor. So there'll be some wording put in there suggesting that beta V only be applied to elements that are expected to yield based on the mechanism for the building. And that wording's needing to be tweaked quite carefully, because we explicitly are not intending for people to sort of go through some iterative approach of saying, right, well, I've run it at 34% MBS and these ones yield, but it's a bit better than that, so I'll do 36 and now tweak the stiffnesses until the cows come home. It's far too precise because we don't really know what the stiffness is, full stop. But if you think that it's a strong column, weak beam mechanism, then applying this modifier to the beams, at least over the key levels where you think the drifts are going to be large enough, seems like a pragmatic way of doing it. Warehouse walls, and I think this to some extent ties into the first question we've got on screen, which is how do we consider C5 out of Wellington for a precast concrete portal frame with tilt-up panels that is built up in 1998? Any particular ductility requirements to be adopted? So we can't probably give you a particular ductility requirement, but can reassure you that changes are being proposed to pick up the fairly well-known issues around some of the connections used between precast panels and their foundations. And so Jason Ingham, Lucas Hogan, and various others have been talking about this issue for quite a number of years now. But I guess reasonably strangely, we don't have any coverage of that in C5 at the moment, or no real coverage to tell you what to do. Fortunately, and slightly prompted by this review, I think Lucas Hogan has pushed out a paper that gives some quite pragmatic ways of looking at these things. And so they've done a bunch of testing on typical panel connections and have observed that a connection rotation limit of 0.02 radians for the connection is about the reliable limit beyond which performance becomes uncertain. And so we'll be proposing to implement that in the guidelines. These panels can be a gravity load path. Some will be, some won't be. It really, I guess, depends as the roof or a mezzanine being held up. And so we'll need some commentary in there as well, pointing out that that's the case and that they could fall into this framework that we've already talked about of gravity load paths and restricting drifts 2/3 of the calculated value. So depending on the situation, a more or less stringent limit, but hopefully something that clarifies how to look at those things and brings some more consistency to assessment of that type of building. Okay, pause there again and just skim over the question. Hopefully the top one, I've given as much as I probably can in that respect. This RC columns detailed for full ductility, 3101. Okay, so the last one, paraphrasing, NZS 3101 allows a KD value of 19 for fully ductile reinforced concrete columns, but the current yellow C5 results in more conservative capacities. That is, well, generally, I guess the assessment guidelines should have the intention of giving either an equal or less conservative outcome than design guidance, sort of a background underpinning. I'd have to check back on the specific situation here. Most of the time, the guidelines do include wording saying where detailing applies with 3101, you can use the 3101 limits if they're more favourable for you, because these things have different experimental underpinnings, and so depending on the data set used, they'll be more or less applicable. I'll try and make a mental note to check back on that one. But there are also, I can't again recall if it was walls or columns, there are a few issues with 3101 limits being, reasonably old now. And some of them have been affected by or shown by more recent research to not work so well, particularly where you have heavy axial loads on items. So there is a possibility that could tie into it there as well. Okay, moving along through, keeping an eye on time because I know there's a number of us on the last flights out tonight, so we've got a while, but a few more slides to go through still. Diaphragms. Spread across parts C2 and one of the appendices and also C5. And I guess this is one of those situations that I alluded to earlier. The elephant in the room for this particular set of changes is that it's a case where early on we said, well, we don't feel that there's enough. We're aware of widespread question of whether the PISA method is right for diaphragms and whether the limitations placed on it are correct or whether they could be expanded or whether something different should be done. And similarly, questions about can we relax treatment of non-ductile mesh, can we clarify what's being done, and so on and so forth. They're both areas where we basically just don't think that there's the knowledge base underpinning things at the moment to make well-based changes that will not be questioned again in a year or two's time. We know it's an important area and really it would push for people to get on and do some more work in that area. It does span, I think, across new and existing buildings, and so maybe it gets picked up in the work related to TS 1170 and so forth. Question over here, yeah.
ASCE obviously has provisions around quite specific and along with the provisions around the design of diaphragms that specific components.
Yep.
We apply those or other basis for those that their requirements are considerably less, both for the design of new buildings and the cheaper existing buildings.
Yeah.
Factors for different typologies of diaphragms.
Yeah. So just sort of paraphrasing the question for those online, is essentially whether thought's been given to the approaches used in US or specified in US documents, ASC 41 and ASC 7, I think it is, that set out quite detailed guidance on diaphragms. Yeah, there certainly have been discussions about those methods and people advocating for introduction of those. The outcomes of the workshops were basically a view that, yes, on paper, those look really good, but no one's clear whether there's no obvious link to a firmer underpinning than what we've got here at the moment. And so it fell into the category of running the risk that, particularly given 1170 has the PISA method in, of introducing a divergence between assessment and design, which is not a problem in itself, but then of changing and then changing again in a few years' time. Yeah. No, I mean, I think there's a very broad awareness that something needs to be done in that space, and we'd love to implement something different in here, but the last thing we want to do is make a change and then 2 years down the track make another change, and have all the fun that comes with that perception of flip-flopping and can't you bloody engineers make up your mind type questions. So what are we proposing to change? Basically, we think that questions discussed aside, once you understand what's going on and with a few corrections made here and there, the existing process for diaphragms is not actually too bad. It's just a bit confusing the way it's presented. And there's this step function that arises that has provoked dissatisfaction and question from a number of people. including myself at various points, and it took some clever explanation to point out that that's actually quite justified and makes a lot of sense and really fits in with step functions that we have, but just glaze past because we're so used to them in all sorts of other aspects of assessment. So we're proposing basically to rejig what's there, but in a way that, subject to some other changes that I'll come to in the next couple of slides, gives more or less the same outcomes, just arrived at in hopefully a clearer way. So putting in some explanation of why the step function is logical and needs to be there, defining the same Pisa envelope, but basing it on base shear rather than overstrength factors, because the overstrength factors really seem like a double handling thing in an assessment sense. They make sense for design because you don't normally work out the full mechanism strength directly, but in an assessment, often you will be and you should be. So why bother then trying to convert that to an overstrength factor to give you a diaphragm capacity? And then sort of in line with that, I guess, reframing some of the steps in C5 to try and link them more explicitly with the Pisa envelope, which I think ties in as well with why the step function's there and hopefully makes it clearer that that does make some sense. So the diaphragm step function, and I'll try to, I guess, explain this in the way that someone lifted the wool off my eyes and I suddenly went, oh, that makes sense. And essentially, diaphragms we assess in the force domain, but we're relying on them to be there to enable the building overall to deform far enough during the earthquake to achieve what it needs to achieve. And that's kind of analogous to shear reinforcement in a beam, which was the analogy put to me, that we routinely look at beams and say, well, is this flexurally governed or shear governed? If it's flexurally governed, then it may have a ductility of 6, but if it's missing a few stirrups and doesn't quite get there, then suddenly it drops down to being a ductility 1 element. And so minor change of stirrup spacing gives you a step function that might reduce the capacity by a factor of 4 or 5. And it's the same sort of thing basically with diaphragms that I apologize for the size of the text on this image, but essentially if you've got a diaphragm and an overstrength demand on a building, the diaphragm is just strong enough to resist the overstrength forces, then the building can, at least in our framework or our way of thinking about things, deform as far as the frames and so forth will allow it to, and the diaphragm's strong enough to do that. But if it's the diaphragm drops in strength just a little bit and the frames can no longer reach their overstrength, then the diaphragm will let go before they really yield and deform as far as they can do, and hence the sometimes quite dramatic drop that occurs through seemingly minor changes of diaphragm capacity. I won't dwell too much on this, but as I say, we're looking at redefining the Pisa envelopes, not in terms of numbers. There are some minor changes because the way the one is defined at the moment for the non-overstrength case is kind of hard to understand what's actually being intended with it. And there is discussion of whether there's an error in it or not, which we haven't quite got to the bottom of, but is resolved hopefully by reframing things so that your diaphragm demand is over either the overstrength base shear of the building, or sorry, the Pisa envelope is either defined by the overstrength base shear of the building, or alternately by a function of the base shear associated with mu 1.25 and SP of 1. People might rightly say, well, that's a pretty weird combination, the mu 1.25 SP of 1. Should that be mu 1 SP1? Or should it be mu 1.25 SP of 0.9? Should it be something else entirely? Should it align with 1170 and be 1.5 times something? All of which were discussed and are valid sort of thoughts. Ultimately, where we landed on that was that there's a background feel, I think, that if anything, diaphragm demands might be on the high side. And so while it's hard to put a specific basis on why it's mu 1.25 SP of 1, that's what it is currently. So in the absence of making or having a sound reason to make a change, we'll leave things as they are. That links into this reframing of step 12, where currently basically the text says if you've got enough strength to resist the overstrength, then you get 100%. Otherwise, use an equation that is a little bit hard to link back to the Pisa envelopes that you've started from. And instead, we've defined some terminology around a bit of an awkward notation, but the Pisa envelope having a demand associated with each floor, and then tying that into the definitions of what the percent MBS rating ends up at. Yes.
There's a specific mention that we have a 4.75 reduction factor for certain analysis. But I mean, there's another sentence that's we just don't need to use that reduction.
Yeah, so the question for those online was around strength reduction factors and strut and tie and diaphragms. And there is a change that's being proposed. So currently, C5 2018 talks about strut and tie in the generic sense and tells you that the strength reduction factor should be as per NZS 3101, take it as 0.75 unless it's capacity design, in which case it's 1. I'm pretty sure there's another section or another line in there that says for diaphragms, take it as 5 with 1 as well. So those things are broadly staying the same. There is another change not mentioned in the slides proposed to back the general strength reduction factor for strut and tie off to 0.85, I think it is, which seems in more line with other aspects of shear type behavior in the guidelines. But yeah, I hadn't put that in here. But does that? That's the proposed suggestion, yeah, that it would be more consistent with how strength reduction factors were adjusted for other things. Okay, moving to a couple of changes that are more material to the actual capacity. So they will change the outcomes of assessments, and we think they should improve the outcome for diaphragms, maybe not by huge amounts in some cases, but anything's better than nothing, right? So collector elements. We've got this K-dia factor that basically increases the force demand on collector elements in a diaphragm. And C5 gives a definition of collector elements. And the concept, I think, is reasonably valid, that the last thing you want is a diaphragm disconnecting from the vertical elements. And if the collector elements connect to the vertical elements, then it's not bad to have a bit more strength for those or to have a lower chance of them failing. But it's probably the case at the moment that that's too broadly applied, in our opinion, and that, in fact, not all collector elements are created equal, for want of a better way of putting it. And so what's proposed is another one of these situations of more of a continuum of things. And so some collector elements are SSWs, quite a very specific definition of elements. For those, K-dia would end up being 2, rather than any implication that K-dia is compounds with the severe structural weakness factor. Then it would be set at 1.5 for collector elements that connect, missing word there, connect to a vertical element that resists more than 25% of the story shear force above or below the diaphragm. And I'll come back to that a little bit more. And then other than that, it would be a value of 1. And so in numeric terms, not too much difference from what's written there at the moment, but hopefully that middle line would mean that suddenly if you're looking at collector elements connecting to one of the many columns in a building, those would not be treated as punitively, because you've got so many of them in most cases that any one is not so important. And I think really we're looking at collector elements connecting into major walls where you've only got 1 or 2 walls that they're particularly problematic. And so the 25% really is judgment based. We're sort of thinking, well, if you've only got 4 vertical elements, then losing any one of those is probably not great. If you've got more than that, then it's not ideal, but it's probably less critical. But, you know, would love comments on that when it comes back as to whether that feels too high, too low. The story shear force was the result of quite a bit of debate about how to define this. And it's really nothing more than a proxy for what we're trying to look at here. It's actually really hard if you start looking at the numbers that would really matter for a collector to actually put down what the value is. And I think we'd all have a similar experience that if you give sort of a variation on the old saying, if you gave 3 engineers a question of what's the diaphragm demand on a particular element, you'll probably get 10 answers back. And so instead, it seemed like story shear force was probably something that we could reasonably agree on between a group of engineers. And more importantly, or as importantly, it's easy to sort of say, well, if any particular element's resisting a large proportion of that, then it's probably pretty important that the diaphragms stay connected to that. So we think this measure will collect or will pick up the collectors that need picking up. It may give the odd false positive, but it will still be a better situation than what we've got currently. Okay, the last diaphragm change that I think talking to before I jump back to see if there are any questions I should be answering, wide cracks. C5 currently has a pretty broad provision saying that if you've got wide cracks in a diaphragm, you should assume negligible shear transfer across those wide cracks, and then links through to requirements in the precast floors appendix about the elongation zone. And unfortunately, that means that often the wide cracks are defined as being effectively along the full length of a frame. And so you suddenly sort of left in there going, well, where do I transfer the shear out of this? And then not really written down, but without any wording to the contrary, the implication seems to be that those wide cracks are there from the get-go in the building. And so no matter how small the drifts are, you're not allowed to transfer shear forces across that cracked zone, which quite frankly doesn't make a whole lot of sense compared to if you walked around any of the damaged buildings down here. Yes, there might be some wide cracks in localized zones, but depending on the demands, they may be the very limited lengths, and certainly not along the full length of the frame in most instances. And that's backed up by some research that's occurred over the last few years. Mike Parr's talked about it in his thesis and also a variety of journal papers where the large frames that some of you will have seen talked about down at the University of Canterbury were pushed and pulled, and the flow of diaphragm forces tracked the various different loading patterns. And essentially a key finding from that was that previous methods for estimating the length of wide cracks just didn't match up with what was observed at all. And in fact, the outcome was much better in the sense of load paths being maintained over much more of the floor plate than would have been suggested by those approaches. And so we're proposing trying to pull that in. The other interesting finding was that really wide cracks do become a problem at a certain point, but you can transfer forces across cracks until they're really, really quite wide. And so what happens is that you get these cracks forming and bits of concrete breaking off the interface of the crack and falling down and wedging in and still providing some load paths. So things get sloppier and more flexible, but you will still get forces across until I think a number that they said was something like 6 millimeter wide cracks. And so it sort of supports the idea that these cracks don't occur immediately, and they'll develop as drift increases, and we should be able to take account of that. So what we're proposing is sort of a collection of criteria saying you wouldn't have any wide cracks to worry about prior to yielding of beams. The maximum length of a wide crack emanating from a corner or from a column would be twice the beam depth. That's more or less sort of a squint at the experimental data. Admittedly, it could be proven to be off base if someone built another big frame with a different beam depth. You know, we only had one beam depth, so the 2 times feels like it's got some logic to it, but it's not necessarily the gold standard, but it feels about right and certainly better than what we have currently. And then how that develops between yielding of the beams or after yielding of the beams depends on the reinforcement that you've got crossing the interface. And so in the normal situation, or probably the more common situation, if you've got some good starter bars crossing that, then we're saying that the full length won't develop until about 3% drift. sort of a pro-ratering between there if that is worth you delving into. Otherwise, if you don't have anything crossing that interface or you've got plain round bars or something, then you'd say the full length occurs at yield. And obviously, conservatively, you could say that it's too much hassle to go iterating and it may not make a huge difference to the assessment outcome. You could jump to that length the moment that yielding occurs, but we feel like giving the information would be sensible for people where it does make a difference. Okay, I'm going to pause and take a quick breather there. We'll try and get through the last slides reasonably quickly, but look at the questions. So we've already talked through, I guess, the strut and tie. There's a question there about strength reduction factors. So as I said, we're proposing increasing that from 0.75 to 0.85 to tie in with the approach of the guidelines. Next question, what would you advise about using red versus yellow assessment documents? The industry guidance that's been out there for quite some time now is basically and remains that the 2018 yellow version of the document is the better engineering advice overall. And so unless there's a good reason to use the red version, so legislative reason, I'd suggest using the yellow version. And I'd also tell clients, and it's sort of a personal bugbear, that the yellow one's not harsher. And for a large proportion or a good number of structures, it will give you a better outcome anyway. And it's certainly not the case that every time engineers revise a document, we look for ways to make things tougher. We're just looking for a better, more realistic answer. Next question, will there be any guidance for assessing pre-stressed concrete? We're about to talk about precast, pre-stressed floors, but I guess you're meaning more generally. The answer is no, we're not putting that in at the moment, unfortunately. But if there are particular things people think need adding, then certainly fire the questions through to the joint committee or technical societies, and it can be discussed and put on the work program if needs be. And definitive guidance on concurrent loading. So the last question is about concurrency and diaphragm demands. The intention there is to clarify things and put in a change proposing to have wording on that. I won't go into what it is because it's still one where there is a wee bit of debate. So I'm not sure which way that will land as to whether the guidance is yes, you should include it, or no, you shouldn't. So we'll see where we get to. Okay, we are on a bit of a time frame now. So precast concrete floors. It won't surprise you to know that we've got a reasonable number of changes on these, a lot of it coming out of the recast floors projects and information gained from there or knowledge gained there, and some reflecting on use of the guidelines and other sort of testing programs that have occurred along the way. I won't dwell on this change other than to say we're proposing putting in definitions of what alpha and beta units are. Most people in this room probably have the fun of knowing what they are, but it seems a bit strange that they're not defined currently in the guidelines. Positive moment failure is probably one of the more dramatic changes that's being proposed. And currently, for those who've had the fun of applying it, we've got this arduous 9-page long procedure for assessing positive moment failure of hollow core units, which is mathematically tough. I suspect easy to make errors and probably provokes debates between engineers when spreadsheets don't match up and so forth. All of that could kind of be forgiven, but it doesn't actually give a good match to what's been observed in experimental testing recently. And so the proposal that's being put forward is to trim things down. So really the actual assessment procedure is not much more. I don't think it even is a page. It's a list of 4 categories of different types of units, and then some tabulated drift limits for each of those. So hopefully a bit more foolproof. You identify the unit, color code up your plan, and then write on a drift limit. And then with an element of circularity, the nice thing is that this procedure does give a better match to the data we've got. And I say there's circularity there because obviously the experimental data informed the drawing up of the table. So it'd be a bit of a shock if it didn't give a better match. but the data is the data that we've got. So until someone comes along with another set, it matches about as well as we can get. And I think that, combined with the fact that it goes from being hours of calculations down to hours to do a full building's worth of color coding and writing in the numbers, is probably beneficial. C5 2018 has this minimum elongation requirement that of 0.5% of beam depth, and even if your frame's not yielding. As I understand it, that was sort of put in as a bit of a placeholder, acknowledging that it probably wasn't right as such, but it was, I guess, at the time, not realised that that would have quite a disproportionate outcome for some of the buildings that are skirting around the earthquake-prone threshold. Obviously, it will affect stiff buildings, but the one that's become pretty clear is if you've got a ductile frame, say, that's down bouncing around the 30 to 35% rating, the drifts at that level will be reasonably small, and so this 0.5% may well impact that quite significantly. So the proposal is basically to take some of the existing equations for geometric elongation, the unidirectional hinge, and use those to estimate the elongation before yield, which has been shown to match pretty well with available experimental data, which is logical. It's sort of nice to see the data. And Frank Bucher has done a great job of putting that together, but it matches up with the logic of the physics or the mechanics going on driving that elongation. A large far-reaching change that's being proposed is to calibrate the overall process, and so look at the so-called factor of 2 that everyone is always debating on the floor assessment procedures. Basically, we need some explanation in the guidelines as to what the precast floor procedures are actually setting out to do. And this is in background data, but it's maybe not so commonly understood. They're not setting out to predict failure or collapse of a floor. The metric used to interpret the experimental data is a 2mm drop at the support. And we've now got a whole lot more data available than when the provisions were written. And so it makes sense to take that data, assess the tested units, and then look back and see how do the experimental outcomes match up with the assessment predictions, and then adjust the calibration factor to get the outcomes that we want from the guidelines. And so again, Frank Bucher has done us all a service and built on an existing database and run through all the units that we have available and plotted out the experimental capacity versus the assessed capacity, and given us the scatter of numbers, which probably more usefully can be put into a sort of fragility format, and without going too much into what fragility curves are, now gives us a ratio of the experimental capacity versus the predicted capacity along the x-axis. So we've got an outlier up here where the experimental capacity was 4 times what was predicted, but the majority of units sort of in the range of a half of the predicted capacity through to twice the predicted capacity, and a scatter along there. And then you can read off a probability for any given ratio up the side. So as written, and I should say written with the proposed changes included, the procedures give about a 35% chance that you're being unconservative. And so basically that means if you take a ratio of experimental to predicted capacity of 1, then you've got a 35% chance of being below that, and having less capacity than you think. The feeling is that that percentage is probably about reasonable. It's higher than we'd accept for failure of a column, but as said, the 2mm drop is not a collapse scenario as such. There are unreliable load paths beyond that, obviously floor units hang up on support cover concrete and things. There are load paths there, we just can't put a number on them or say how reliable they are. And more questionably, I guess you can say the floor unit, the area of a single floor unit is less than typically supported by a column. I guess that's counted by the number of floor units being higher. don't know quite how the statistics play out on that. But so essentially the proposal that's being made is that the procedures as written are pretty good, give the outcome roughly that we want. And so we only need a factor on there to account for the fact that we don't want, we're not just thinking about the ULS earthquake, we're worrying about something bigger than that. And so that would, if accepted, lead to replacement of the factor of 2 with a factor of 1.5. Okay, couple of slides left. Where to from here, basically? So I guess one question that comes to most people's minds is what's going to be the outcome of these changes? And we don't know quantitatively yet. There's not been any rigorous comparison of before and afters on any particular buildings. There are discussions being progressed about trying to reuse some of the previous C5 evidence project work from back about 4 years ago, where various consultants looked at different buildings with red and yellow C5 and what the outcomes were. We're hoping that some of those reports might be dusted off and used to then look at what these changes would mean. Qualitatively, one of the workshops looked at things and said, well, probably overall, most of the changes will improve assessment outcomes, so scores will be higher using the new document. And I think that plays out. It's pretty obvious if you reduce the factor of 2 to 1.5, then floors will generally be better, and various other changes in the same. So that's sort of where we think things will land with this. What's the next process? Probably some more lively debates. The next step basically is some tweaking of a few of the changes to reflect previous feedback, and then a formal balloting by a committee of experts on the subject matter to hopefully get buy-in that these are reasonable changes to propose, after which they would presumably be intended to be published for a public comment phase, I guess somewhere around the middle of the year, with feedback sort of sought on what's being proposed. Finally, really, just a load of acknowledgements. I won't read all these names out here, except they're partly here to reassure you that a lot of very wise and educated people have had a lot of input into this process. So there's been a fair amount of thought to it. I would like to call out Frank Bucher again, for going above and beyond, I guess, even beyond the end of his PhD studies and helping pull some data together in ways that have really improved a lot of the precast floor proposals. And obviously we need to thank MB for the financial support and also the permission to talk about this at this sort of stage of the process. So yeah, we've got a couple more questions. Oh, one we've already dealt with. This one question popped up, couple. So I'll go to those ones on the screen while you think if there are any in the room. I think there's a number of us here. We'll only be able to be here for about 5 minutes, but what have we got up here? When are we expecting the final document? Don't know. I guess hopefully this year would be the aim. It's sort of in MB's hands of exactly how the process plays through. And any chance of guidance in C5 on loss of punching shear capacity of drop panel slab column connections? That question maybe might be one, if you could email me about that question. I'm sure you can find an email address for me through the CSOC website or otherwise. My immediate question is the chance of getting punching shear guidance. There is punching shear guidance for slab column connections in yellow C5. So probably need to have a discussion offline to get more into the details of that. Yeah, question in the room.
Well, the guidance provided clients as to how to scope and divide, because I mean in Wellington there's a lot of fatigue, obviously. You know, these are great guides, but almost everybody to like 60. So
Yep, no, great.
So are there ways to, you don't want someone just cherry picking the good stuff and leaving out the bad, but
Yeah, so the question is how do we bring this into how do you practically and efficiently, I guess, bring this new knowledge into situations where large amounts might have been spent on existing assessments? And it's a really good question. I'd imagine there will be guidance put together. It's not been done yet. I don't know whether that'll be tech societies or MB. It'd probably be a joint committee thing to sort of think about how that's done. The comment I would make is that really overall, I think when we went through the change or the big changes sort of line by line, almost all of them are on the positive side. So it's actually not really a situation where you can cherry pick the good ones and leave out the bad ones. But I guess it's going to be situation dependent. You could pull out the precast floor stuff, I guess, and you know, hopefully reasonably efficiently relook at an existing assessment, say, well, that was done with a factor of 2, it's 1.5 now. What does that mean? But yeah, it's a huge part of why we've got the 2 sets of assessment guidelines and why it's taken this long. And people really need to think about how we get updates brought through.
Mesh. Oh, sure.
Yeah.
Has anything been changed for cold run mesh diaphragm capacity?
No, the feeling of the group reviewing it was that what's really needed is some industry examples of how to deal with cold drawn mesh and develop a consensus on the existing provisions that way, rather than trying to wordsmith things to bring precision in. So people are reasonably happy with the wording that's there. It's just getting a consensus written down of how it should be applied. I think looking at the time, we will have to draw things to a close. Those of us heading for the 8:45 flight, cutting it slightly fine. But thank you all for coming along. Thank you for being at the AGM. And yeah, happy to take questions via email or whatever as well. So do reach out.